In this lesson, we're going to explore the idea of the volume of a sphere. To understand where the volume of a sphere comes from, what you have to do is you have to break apart a sphere into little, I'd say little pyramids shapes. They're really not pyramids because this end piece right here is a curve. So what you do is you would break up the sphere into little pyramids as small as possible so that this curve is as small as possible, making it closer and closer and closer to a true pyramid. And then what we know about a pyramid is that the volume of a pyramid is 1/3 the area of the base times the height. Now, when we break that up and pull those pyramids out, what we have to understand is that the height of that pyramid, because we're pulling those pyramids out and the point at the very tip or the vertex of that pyramid is at the center of the circle, the height of that pyramid is actually the radius of the sphere. So we're looking at 1/3, the area of the base, whatever that first base is here, times the radius. And we would do that for as many of those pyramids as you need. So we look here, we got base 2 times the same radius, and we would keep going until we had the last base, that's an L down there for last, times 1/3 the last base times the radius. Now, algebraically, what we could do with this is we can factor out the 1/3 r, because that's the same and that's common amongst all of these little volume equations for those pyramids. So if I take out that 1/3 radius, what that leaves me with is the area at base 1 plus the area at base 2, all the way up until I get the area of the last base. Now, if I add up all those bases, because those are all coming from the exterior of the sphere, what that is equivalent to is the surface area of the sphere. They would all add up to the surface area of the sphere every single time. So what we have here is we would have 1/3 the radius times the surface area of the sphere, which is 4 pi r squared. So if we clean this up a little bit, 4 times 1/3 is 4/3. We have a pi involved here, and then we have r times r squared, which combines together to give you r cubed. That is our formula for the volume of a sphere. So we now know the volume of a sphere has a formula that is 4/3 pi r cubed. So what happens when we look at a hemisphere? Looking at the area or the volume of a hemisphere, coming from a surface area perspective, it's a lot easier, because truly all you're doing is you're cutting the amount of substance in that sphere exactly in half. So if we take the volume of a sphere, which is 4/3 pi r cubed, and we want to take exactly half of it, so we're just multiplying it by half. Really, the parentheses are not necessary there. I just kind of put them in there. But as we simplify this down for the volume of a hemisphere, half of 4/3 is 2/3. So if we are given a hemisphere, whether it's freestanding or connected to another object, we're looking at 2/3 pi r cubed for our formula. We're going to skip over some of the more basic type of problems, and we're going to jump right into something that has a little more substance to it, like this question here, where you're giving this green sphere, and you got a circumference that is 24 inches long. Obviously, the answer that we're looking at the very end is going to be 233.4. This is a sample question from one of our textbooks. So how do you get that 233.4? So being that they gave you the circumference of the great circle, we know that circumference is equal to 2 pi r. So if we plug in the 24 for our circumference, we are able to solve for r, find out the radius of our sphere is, and then calculate the volume of that sphere. So we would divide both sides by 2 pi. Our 2's would cancel, our pi's would cancel. We're going to get a value for r. Now when we take our 24 divided by 2 pi, you have to make sure that you divide by 2 pi in parentheses. Remember, 2 pi is approximately 6. So 24 divided by 6 is 4. So we know our answer for this should be approximately 4. If we divide that out, we should get exactly 3.8197. Now we're going to take that radius and we're going to use that to calculate the volume of our sphere. So we're going to jump to our volume formula, which is 4/3 pi r cubed, which would be 4/3 pi times 3.8197 to the third power. If we go ahead and type that into our calculator, you should get approximately 233.4 cubic inches. So here's a good higher level question. Suppose you got a sugar cone that is 10 centimeters deep and has a diameter of 4 centimeters. You have a spherical scoop of ice cream with a diameter of 4 centimeters that rests on top of the cone. Our question here, that's numbered question number 21. If all the ice cream melts in the cone, will the cone overflow? Obviously, it's a volume question. Is the volume of the sphere big enough so that when it melts into the cone, that it will overflow? There's not enough volume in the cone to handle the volume of the sphere. So we're going to find the volume of the cone first. So that would be 1/3 pi r squared h times the height. So we got 1/3 pi times 2 squared times the height, which is 10. We calculate that out, we should get a volume of 41.89. And that would be cubic centimeters. So there's the volume of our cone. Second thing we would do is we would find the volume of our sphere. Our volume formula here is 4/3 pi r cubed. So we're looking at 4/3 pi times 2 to the third power. If we calculate that out, we end up with 33.51 cubic centimeters. So obviously the volume of the cone is a little bit larger than the volume of the sphere. So if that scoop of ice cream completely melts, the cone should be able to handle that sphere of ice cream. So we're good to go there. Now, for 22, if the cone does not overflow, what percent of the cone will be filled? So we got to find the percent of the cone that will be filled. So we're looking at how much space is taken up in the cone, which is 33.51, over the entire cone, the larger object, which is 41.89. Again, looking back at our geometric probability, we're taking the part that we're focused on divided by the full object. So the part we're looking at is the volume of the sphere that's melted inside of the cone, and the total object, which is the volume of the cone. If we divide that out, you get 0.7 followed by a whole bunch of nines, and then some other digits after that. So we're looking at approximately 80% of that cone being filled. In this example, what we're doing is we're starting off with the surface area of a sphere. They tell us that the surface area of the sphere is 784 pi square inches, and we're asked to find the volume of that sphere. So, to start off with, if they give us the surface area, they give us anything, really our goal when we are working with spheres is to find the radius. So we're going to start off with the surface area formula for a sphere, which is 4 pi r squared. We're going to substitute in our 784 pi. Very nice of them to leave it in terms of pi for us. You'll see here that it helps us out algebraically, because to solve this for r, what we're going to do is we're going to divide first both sides by 4 pi. So our 4's cancel, our pi's cancel, and we are left with r squared. On the left side here, our pi's cancel out, which is why I really like that they left it in terms of pi for me. And then we take 784 divided by 4, which is 196. We would then square root both sides. Algebraically, we would end up with a positive and negative 14. But because we're looking at a unit of measurement like a radius, you cannot have a radius with a measure of negative 14. So we're only going to focus on the positive answer there, which is a positive 14. Now that we have that radius, we can go ahead and find our volume. Our volume is 4/3 pi r cubed. So that's 4/3 pi times 14 to the third power. And if you calculate that out, you end up with 11,494. And the units would be cubic inches. For our final example, what we're going to look at is we're going to want to find the radius of a sphere that has a volume of 160 cubic inches. So to start this off, we're going to start off with our volume formula. 4/3 pi r cubed. We're going to plug in the 160. It's not a very nice number because it's not left in terms of pi. Sometimes it may happen that way. Now, algebraically, what you want to do here is we want to get rid of that 4/3 first. So we're going to multiply both sides by the reciprocal, which is 3/4. On the right side, the 4's cancel and the 3's cancel. On the left side here, as we work through this, we're looking at 160 divided by 4, which is 40. 40 times 3 would give us 120, equals pi r cubed. Now we still have to move away the rest of the multiplication here, so we're going to have to divide by pi. Which will isolate the r cubed. So 120 divided by pi puts us at 38.197. And now, This is the reason why I selected this example right here, is because we need to talk about how do you get rid of a third power. Often at times when you get to this point in geometry, you've forgotten about how to remove a power like a power of 3. It's not the square root of something, but the cube root of something. So I want to show you that cube root here on the calculator. Cube root of r cubed is simply r. The cube root of 38.197, I pull up my calculator here, I can go under the math menu, and option number 4 is a cube root. And then we can enter in our previous answer here, boom, and we figure out that, oops, let's take that pen off of there. And we can figure out that our radius for this problem should be 3.37 inches. And that's it. Good luck on your assignment for this.